So, good morning, everyone. Thank you very much for joining our webinar today. Today's webinar will be about the principles of qPCR and how we can use the qTower PCR system by Annelieke Jena to provide us with the best possible results for our experiment and make sure we can impress all our colleagues with the results we get. Today we are joined by Matthias Ludwig from Annelieke Jena. Matthias has been with Annelieke Jena for the better part of 15 years now as an application specialist, and right now as a senior application specialist. And I feel very confident in saying that he is probably the world's biggest expert when it comes to qPCR on a qTower system by Annelieke Jena. Matthias will be walking us through the applications of the qTower system and some other application matters. Before I hand over to Matthias, one thing I would like to say is that if you have any questions during the course of the webinar, please feel free to write them in the Q&A box. You can find the Q&A box on your top left in the taskbar of the Teams application, and we will be making sure to go through all the questions that you have at the end of his presentation. So with that being said, Matthias, please take it away.
Thank you, Martin, for the flowers. Yeah, I'm not quite sure that I'm so a good expert, but yes, I work a couple of years with not only with the qTower, I work a couple of years in the area of qPCR. And now I would like to show you or give you some ideas what you can do not only with our qTower, but what can you do with the real-time device? What kind of applications are possible and what are is also common. So we have our qTower family. And I have a little bit of order. We start with absolute quantification, that's so the basic one, then also the delta-CT method, genotyping and melting curve. These are also the basics. I will not go deep in detail about the standard one, this yes and no statement, this qualitative analysis. This is so the standard of real-time PCR. This means if you get in curve, you know, yeah, my target is inside. If you get no curve, then you know, okay, my target or my sample is not inside what I'm looking for. So, okay. Annelieke Jena is a manufacturer of devices, and for example, of our real-time devices, our qTower 3. We are not a manufacturer of detection assays or master mixes, and so we are free, and also you are free what kind of master mixes, for example, for real-time PCR you use, and you can use your own in-house assays, but I will give you also some examples from other suppliers. So that you get an idea, okay, that's a totally open system. And we offer this device in, or we have different kind of devices. We have a standard 9612 format. We have it as also in a standalone variant. It means with an integrated display. And we have also in 384 well format device for higher throughput. So the classical real-time PCR workflow is so that you start with your sample preparation. This is in principle also like the bottleneck, because if you have not a good sample preparation, or you isolate, or you can you purify nothing, then it's also not possible to detect anything on the bag. And it's also good to have a very, very clean sample without inhibitors, because this can have also an effect of your data analysis. You can get false negative results, for example, and this you have in your mind that the bottleneck is in principle the sample preparation. And it's up to you if you use RNA or DNA samples. You can use total RNA. You can use also a small RNAs, microRNAs, and also for the DNA, that could be specific sequences. That could be also whole genomic DNA. It's up to you what you extract. It could be comes also from plasmids. There's no limitation. Then you have to you start with your qPCR setup. In principle, you choose the assay chemistry. That means you can choose between intercalating dyes like cyber green, Eva green, and also Ethium bromide. It's also an intercalating dye. Or if you use with probes, fluorescence probes like Techman probes, this is your choice. The device can handle both of them. And there could be possible that you need an assay or probe design if you use not commercial assays, or if you use not assays that are published. Yeah, then it's possible that you need an assay or probe design or an assay optimization if your results are not or looking not so good. So then you have to select the thermocycling. We use the real-time fluorescence detection. That means we work with intercalating dye or with Techman probes, and we use this real-time detection with fluorescence. And last but not least, this is then you can see some curves, but important is to know what is my analysis in the back? What is my goal? You can have a qualitative analysis. That means a yes and no statement. You see a curve, yes, or you see no curve. This is a qualitative analysis. Or if you want to have a quantitative result, it means the absolute number of copies or concentrations, or if you have a melting curve analysis or other things. Yeah, the data analysis on the back is also very important, but in principle, it's up to you what you want to do in the back, because the data analysis is based on the raw data, and this raw data will be collected here on the thermocycling. So, okay, we start with in principle with the simplest one. This is the absolute quantification. And for the absolute quantification, you use this method for the determination of absolute copy numbers of nucleic acids. You can use unknown samples, but you need for this quantification and calibration on standard curve. And this is then necessary to create such kind of standard curve. You need samples with known concentration. And then you start with the serial dilution. And you can use external standards. Synthetic standards are recommended because synthetic standards are stable, are independent of the quality of the extraction, and this is the advantage of a synthetic standard, like in positive control. But you have the information about the stock concentration to start with the serial dilution. You can make an logarithmic dilution and half logarithmic, whatever you want. It's only important that you input inside the software the concentration of your standards. So, in principle, synthetic standards could be RT-PCR products. That means reverse transcription products, plasma DNA, in vitro transcripted RNA, DNA oligonucleotides, or RNA oligonucleotides. These are possible for synthetic standards, but you can use also your in-house or your own standard. That means you extract it and you have in stock or your own culture. Important is you have an information about the stock concentration. So, and then in principle, the most softwares create based on the CT values and calibration curve with the important calculation numbers with the Y and the X, and then also with the R square information. And the best is if you have an R square around about 0.98 or 99. The best one is 1.0. This gives you the information how good your spots or your real samples are located on the imagined calibration curve. So, and all this informations will go into the formula, and then the software calculate for you then not only the R square, the software calculate for you also the efficiency of this PCR, and this could be help also for your assay design or for your PCR protocol, and then you get an idea how good is my PCR working. A good efficiency is in a range between 90 and 105%. Yes, in principle, it's only a theoretical value because more than 100% in principle not possible, but this could become from the effects of round the numbers or the values. So sometimes it's also acceptable to have an efficiency lower than 90%, but my recommendation is please look that it's not less than 85%. So, and then you have to know, maybe you have some inhibitors inside, or you have to change the concentration of your samples or your primers and so on. So, these are the basics. And how it could looks like, or what could be an application is, for example, the detection of SARS-CoV-2 load in wastewater. And this is also an example what we used here in our lab, and also a lot of customers in Germany work with this application. That means they extracted the nucleic acid or the virus nucleic acid from wastewater with our InnoPure C16, and then for the detection they used the Promega GoTag and Wire wastewater SARS-CoV-2 assay. And this assay is also inclusive of a synthetic standard. That means the customer or you have to be or can use directly this standard and have not looked for their own standard. And so we have the known concentration, and you start with the serial dilution. That it's an logarithmic serial dilution. And then you input into the software, and then it could be possible that you can have get such kind of results. This is the monitoring spot, and the software calculate and also a standard curve based on the CT values. And we showed then also this, for example, for N2 target. And inside this assay, you have also the possibility to detect N1 or E gene, and also PMMUV. And for this, 3 different viruses or targets, you can create a calibration curve. So, and you can see here we have an R square of 0.999. And we have also a very good PCR efficiency of around about 94%. So, and based on this calibration curve, the software calculates for you the unknown, the concentration of the unknown samples in and based on this one. Another one could be comes from the food market or plant research area. This is for the detection of the GMO load or ready Roundup load inside genetic modified organism or plants. Or to check, is there a ready Roundup load inside my food, for example. And also here we extracted the samples from plant, from plant material, and then we used the SureFood GMO quantification assay, in this case from the company Congene. And we used also the Q-tower again, and the feature of the absolute quantification. And also here is it so, there is a positive control with known concentration inclusive of this assay, and you create a serial dilution, and based on the serial dilution of this soy and this ready Roundup soy, the software can calculate the load of this ready Roundup soya inside the unknown samples. So you have 2 positive controls inside, and so you have to perform two different calibration curves or standard curves, and the software can calculate this. And you can see here that's based on the CT values. The software calculate the copies of soya for the different extraction, for example, and also how many % of genetic modified are inside the soya. And you can see here we have around about 50% of already round up inside this corn. So, and here a little bit lower level. So, okay, this is for absolute quantification. The next, and it's been also very popular, is the delta CT quantification. And this is in quantification what it's often used in research areas at universities, because here this quantification tool is would be used for the determination of expression factors or ratios for different groups, for housekeeping and also for my gene of interest. And this is to detect is a gene switched on or off, or how is the reaction of the organism of different environmental issues or changes. It could be difference in the pH value or in the or if maybe insects are on plant materials, and they switched on some parts of the genes to produce or manufacture some metabolism and so on. And for this is this delta CT method useful. You need here not directly in calibration curve, that it's possible to work with the calibration curve, but in principle it's also okay to have a calibrator. And this is like in control group. It's in group without treatment. And you have a calibrator for your gene of interest, and you need a calibrator for your gene of reference. The gene of reference is a housekeeping gene. You can have also more than one gene of references, so you can get better results. So, but if you work not with a calibration curve, then a calibrator is necessary. Yeah. So, and there were also two different methods available on and also published. This is, for example, the LIVAC method. This is then without the PCR efficiency. Yeah. Then you do not need a calibration curve or a standard curve. For a better accuracy, is the FAFE method more recommended, because you have then a calibration curve for your gene of interest and also for your gene of references. And then based on this PCR efficiency, the software can use this information for a more accurate calculation of your gene expression factor. So we offer inside our software both methods, the LIVAC and also the FAFE method. In the LIVAC method, is it so the calculation is then based on an efficiency of 1 or 100%, and in the with efficiency you can change this, or you work with a calibration curve. So in principle, this is the calculation, the basic of the calculation. You start with the first delta, this is the CT of your gene of interest for your sample, for example. The first delta is our sample CT or delta. We subtracted from the CT of gene of interest, the CT of the gene of reference. And the second delta CT is then for our calibrator. That means the group without treatment or the control group, and also here from the gene of interest and the gene of reference. So, and then we create a delta CT, and you can see here the delta CT from the sample and the delta CT from the calibrator. And then we get the n-fold expression of the sample to the calibrator. So, as an example, for example, here for immune system gene and influenza. This is in people with influenza and in people without influenza. We used a gene for the immune system. This is our gene of interest. And then housekeeping gene, and then you have here as an example human with influenza, and the calibrator is then a human without influenza. And this could be some curves. You have here different CT values, and this CT values goes then inside this calculation. This is what the software will do for you. It's not necessary that you have to do this by yourself. So the software calculate, and you can see here without efficiency, we have an expression factor of 5.7. And when we work with efficiency, we have an additional values. Yeah, we got a more, it's less than, but a more accurate expression factor, and this is 4.5. So, and so you can see there is an effect if you calculate with efficiency, the Pfaffel method, or without efficiency, the Levac method. So we have also some other practical example. That's also we used or we checked the expression factor of tobacco if there are insects or on this tobacco located. We isolate RNA, and we developed our in-house assay, and we use then here we get also information about the gene of interest. And these are the curves of our reference gene. And you can see here this is a very good gene of reference. And here we have different expressions. You can see then here also the results in a bar chart. This is the normalized expression. Yeah, it means normalized expression is related to the calibrator. And then you get also an information about the relative quantity. If you work within calibration or with a standard curve, then the software can also calculate for you the relative quantity of this RNA load and also of this of the results. So, and the software can give you these bar charts. But we have also this comprehensive data calculation. That means it's not necessary to export the raw data. Everything what you need for delta CT quantification, calculate the software for you. Yeah. Based on the CT values for the gene of interest, for the reference gene, we make also like a mean CT. It means when we work with replicates, we show then the delta CT, we show the standard deviation and also the normalized expression. Here you can see this under-regulated, this is higher regulated when it is higher one or lower one. And so you can get an idea about the regulation of the genes. So, okay, this is for the delta CT quantification. The next one is genotyping. And genotyping is often used for the determination of different alleles, like wild type and mutant, to get an idea, is it homogeneous or is it heterogeneous? And you can, this is then, or for this, you need a multiplex assay, a duplex, triplex, or more than one. For other ones, would it be possible to have also like in singleplex for like quantification and also for delta CT method? But here, for the genotyping, you need a multiplex, minimum and duplex for the two different subtypes. That means you have you work then with different fluorophores. Yeah. For example, one fluorophore for our wild type, one fluorophore for the mutant. So, and they have to be different. Yeah. And to detect then also the different signals. Yeah. This is then a question about the assay design. So, and in principle, so if you have a homozygous wild type, you get only a signal for this fluorophore number 1, for example. And if you have a homozygous mutant, then you get only a signal for this for the other fluorophore. And if you have a heterozygote sample, then you get both signals. So they can have the same intensity, but it's not necessary. It could be also a little bit different. It's depend on the fluorophore. So, but then you get definitely two different the signal for the both alleles, because it's heterozygote, or you get only one of this both signals for fluorophore 1 or fluorophore 2. And then you know, okay, this is homozygous. Yeah, so. Also for this, we have some examples. It would be also often used for the human diagnostic in hospitals, for example. Here it is. It's also from a customer from us. He used in clinical human samples, and they detect for factor 5 Leiden. This is for thrombophilia, and it's so that patients with this factor 5 mutation have more and deep vein thrombosis. So, and this is then helpful for the therapy. And also for before they go in or they get an operation so and get some medicine, then it's good to get an idea. Okay, it's factor 5 wild type or heterozygote, and to get this kind of idea. This is a commercial assay. It's not an in-house. It's a commercial assay from the company Vienna Lab from Austria. And in the software, it's impossible for a very smart few to get such kind of scatter plot. For example, for factor 5 mutant, factor 5 wild type, and then you can see here directly which sample is homogeneous for wild type or mutant, or which sample is heterozygote, have both types, and which sample have no CT values, no targets, or any issue. Normally, only the NTC should give no signal. And here it's also possible to get an information like in chart. Yeah, and then you have here also the information about the different genotypes. Is there a CT value, yes or no, a statement? But we show them also in principle the CT values. And the software calculate for you based on the results. Okay, I have here, for example, and yes, and that means in CT value for genotype 1 and 1 for the and also for genotype 2. And the software calculate and gives you the information. Okay, this is heterozygote. So, and if you have only information for genotype 2, the software knows, okay, this is factor 5 wild type. And if you have only information about here genotype number 1, the software knows, okay, this is homogeneous for factor 5 mutant. So, and then we give you also some errors or failure, for example, because we have no CT value. The reason could be there's any issue with the extraction. There are some inhibitors, because in principle you should get a signal for one of these two different alleles. So the second sample, it's also a detection assay from the same company. So is to detect two different genotypes. Yeah, for lactase persistence, and also here. The customer used the clinical human samples, and then they need here only two different color modules, and then they can say, okay, this patient have a multigestion of lactose, or that means there's lactase non-persistence, or it's a standard, or there is here, as it's this have this lactase persistence. So. And here, the software detect, or the assay detect two different genotypes. These are also part of this assay. And then you can see here, based on the scatter plot or this endpoint signals, if you have a patient with lactose intolerance or not. And this is, for example, important for the food, what you give into the patient in the hospital, and also for the patient then later, that they know, okay, they have to avoid milk products, or they have to buy specific lactose-free products, and so on. Because there's a main difference between lactose intolerance, or people they have some digestion issues with lactose. So to detect is there in really lactose intolerance, you need such kind of genotyping. So, okay, yeah, and you can see here this is like an allele discrimination. And for this, you can also use this genotyping tool. Last but not least, melting curve analysis. It's not so simple in principle, yes, but you can do with this melting curve experiments or analysis also some specific or new things. In principle, it is so it's useful for intercalating dyes. And it is then for the determination of fragments lengths. That means if you have a shorter fragments, you have a lower melting point. If you have a longer fragment, you have a higher melting point. Or if you check the quality of your assay to get information about primer dimers or primer, or mismatching or unspecific products. For this is also recommended when you create your own assay for the primer or for the assay development or assay optimization. It is recommended to work in the beginning with the intercalating dye and make a melting curve experiment to get an information about the quality of your assay, to see if there are primer dimers or if there are a lot of unspecific products. So, yeah, here for testing of primer dimers, but you can use a melting curve also for protein analysis, like the thermal shift assay. So, in principle, it's so you have, for example, here the intercalating dyes. They are double-stranded DNA, and when you start with the melting curve, we heat. We increase the temperature in the sample from cycle to cycle, and when it's then denatured the fragment, the intercalating dye is not more inside the double-stranded DNA, and the fluorescent signal decrease, because you get only a fluorescent signal if the intercalating dye inside the double-stranded DNA binded, and if you have a denaturation step, then the fluorescent signal decrease. So this is then a typical curve of a melting experiment, and you can see here two different shoulders, and the software calculate for you then, and you can get here some peaks, and this peaks gives you the information, okay, here about the melting temperature. For example, here we have a lower melting temperature compared to this one, and this is gives us the information. This is a shorter fragment compared to this one. So, but the other ones is to work with proteins. Then if you have a native protein, you have no fluorescent signal. The intercalating dye, this could be cypro orange, acrinidine orange, there are specific dyes outside. And then depend on the pH value or others or salt concentration. And when we increase then the temperature, we have a defaulted or denaturation. So, and then this dye will be bind and inside the protein, and then we can detect a signal. So, and this looks then a little bit different. I can show it to you. For example, this is for example for different fragments. Yeah, you can get here. These are different primers, for example, the same sample but different primers, and then you can see here we got then different fragments. And depend on this, we can select. I can select, for example, which primer pair is for me the best choice, or is there sometimes also any issue that I have primer dimers? Yeah, you can see here a lot of different temperatures or melting temperatures. For a thermal shift assay, it looks a little bit different. Here you have an increase of the fluorescent signal, not a decrease. When you work with cybergreen, you have a decrease during the melting curve with the proteins, and with this cyber orange, for example, you have an increase of the fluorescent signal. This is the reason why you have to flip this curve, and then you get here also results for the different proteins. For example, this melts or denaturate a little bit earlier because of maybe the salt concentration, or this could be here different salt concentration. This could be also different pH values. And then you get here information about the stabilize, how stabilized is this protein in these different conditions. So there are also a publication available with this different for such kind of example. So yeah. Okay. Thanks for your attention. This was an overview about different applications with our device. And you can see it depend on, it's in principle independent what is your starting material. With the real-time PCR device, also with our qTower, you have a lot of different possibilities for downstream applications, from absolute quantification also up to melting curve or genotyping. It's up to you what you want to do. Yeah, so. And now feel free and ask questions.
All right. Thank you very much, Matthias, for this informative talk. I see we do not have any questions in the Q&A box at this time. I will give a few minutes for people to maybe type a question if they want. But in the meantime, Matthias, like I already mentioned, thank you very much for giving this very informative talk on the capabilities and the applications of the qTower system. If any of you watching at home or in the office have any questions that might come up at a later time, because very often the best questions come up after you've closed your computer down. If you have any questions that come up at a later time, please feel free to reach out to us at any point. You can reach out to either me directly or to Annelies de Giena, and we will make sure to support you in the best possible way and answer any questions that you have. We will make sure that the presentation is sent out to all attendants that have registered, and the presentation, the webinar, will also be available on YouTube from today. Again, thank you very much for attending, everyone. We will be making sure to send out a registration of the webinar. And like I mentioned, if you have any questions, please feel free to reach out to us. Have a nice day and good luck running qPCR experiments in the future.
Yeah.